Hello, everyone. As we all know, humans exhibit a remarkable ability of understanding what is being said in different contexts. So, for instance, if I played you this audio,
I'm on my way to the meeting.
I'm on my way to the meeting.
so these are two different talkers that said the same exact sentence, I'm on my way to the meeting. However, if we looked at their spectrograms, we can notice a huge variability in both signals, which suggests that the same speech content can be acoustically realized in so many different ways. And that poses a computational problem because there's no clear one-to-one mapping between an acoustic signal and its corresponding speech or linguistic units. So while human speech recognition is robust, we know that humans are quite vulnerable to hearing loss. And our goal is to build a model of human speech perception that can help us better understand and inform new treatments of hearing loss. So there has been a plethora of computational models proposed of speech perception from both community, psychology, and engineering communities. However, all of these models might not be good candidates of human continuous speech perception because some of them don't rely on acoustic inputs. Others are constrained by a fixed vocabulary, so they cannot recognize new words, unlike humans. And some models don't account for the continuous nature of speech. And with the recent ASR systems, it's difficult to do science with them because they're either not open sourced or it's difficult to train them from scratch to instantiate hypotheses about how humans perceive speech. So these limitations invite the following questions. We ask if we can build a candidate model of continuous speech perception, and if that model can generate would generate human-like patterns of responses and errors. And if we can eventually use that model to help us understand the role of context in speech perception. So to start off with the first question, we trained a model that learns a mapping from a variable acoustic signal into its constituent subword units, whether characters or phonemes. And the training paradigms goes as follows. We compiled a large set of speech corpora that has text labels associated with them, and then we used the text labels to train the model to predict a sequence of characters. And for phonemes, we transcribed all the text labels into phonemes using a text-to-phoneme model, and we trained our models to predict a sequence of the generated phonemes. We trained the model on around 7.5 million utterances, corresponding to a total of 15,000 hours, and we call that model Parrot. So Parrot, it consists of an auditory periphery model that converts an acoustic signal into a cochleogram. We feed this cochleogram into several convolutional layers that followed by several recurrent layers to learn contextual representations. Then we use a linear decoder to map these contextual representations into a probability distribution over the subword unit of interest, whether characters or phonemes, through time. After training the model, we evaluated it on an existing phoneme recognition benchmark against other ASR systems. And here we're reporting phoneme error rate, so the lower the value, the better. And as you can see, our model in teal is showing competitive performance with state-of-the-art ASR systems. So then we asked the question if that model would generate human-like patterns of responses and errors. To do that, we needed to design a new behavioral experiment that can enable us to compare humans and models on speech perception tasks. So we developed a spoken non-word recognition experiment where we use real English words and via a pseudo word generator, we generate non-words. So these are words that don't have any meaning. However, they are phonotactically plausible in American English. And we synthesize these non-words so they sound something like this.
Prender, Downbro, Nubmeeb.
And the task goes as follows. We play these non-words to human subjects and ask them to write down what they've heard. Then we transcribe what they've written into phonemes. And that would be the human prediction. We do the same thing with the original non-word and we transcribe it into phonemes so that way we can compare human performance, evaluate human performance. And we do the same thing with our models, and our models would generate phoneme predictions, and that way we can compare humans and models on a phoneme level and look into patterns of errors and mistakes they make. So we ask if the model can match human level performance. So we tested humans on models on around 5,000 non-words, and as you can see here, that humans seem to be slightly better with a lower phoneme error rate compared to our models. However, both models and humans are within striking distance in overall performance. Then we wanted to see if the model would actually can actually generate patterns of phoneme confusions relevant to humans. To do that, we looked at the human phoneme confusion. So here we're reporting the true phonemes on the vertical axis and the predicted ones on the horizontal axis. And you can see this is the pattern of mistakes that humans made on the task. And we can see a similar pattern of mistakes in both our models, whether optimized on characters or optimized on phonemes. So here we show for the first time a full confusion matrix for humans at scale that enable the first systematic comparison of models and humans on a phoneme level. So to quantify this qualitative similarity, we looked at the off-diagonal correlations, and here you can see that there's a high correlation for both models with human phoneme confusions, suggesting that the model was able to replicate patterns of human mistakes. So we ask if the same pattern can be captured using a simpler model. To do that, we ablated the context-based mechanisms in our original model, generating a smaller version of our model, which we refer to as mini parrot. And indeed, we see that there is a significant drop in the human model alignment, suggesting that the pattern that we captured in the first place was not a trivial pattern to be captured and required a complex system. So then finally, we ask if the model can help us understand the role of context in speech, specifically the directionality of contextual processing in human speech perception. So we know that phonemes are produced differently depending on the surrounding context, and that's because the effect of co-articulation. So the target phoneme is the acoustics of the target phoneme varies as a function of the preceding as well as the following sounds. However, it's unclear whether context plays a role in human or the context before or after a phoneme plays a role in human speech perception. So to measure that, we manipulated the direction of contextual processing in our models and identified the direction of context that best explain human variance. So to do that, we trained three variants of our model. One that is acausal, that has access to both past and future cues. Another one that is strictly causal that only has access to past cues, and a third one that is anti-causal, where we reverse the speech signal and that model only has access to future cues. And as we see here, the acausal system was the one that performed closely to humans on the non-word recognition task. And when we look at the confusion, when we look at the patterns of confusions, we see that indeed the acausal system was the one that aligned more with human phoneme confusions, suggesting that humans might be relying on bidirectional cues within a local window in order to make prediction about the target sound. So in conclusion, we propose a new class of speech models. These models allowed us to instantiate new hypotheses about how speech is encoded in brains and minds. We also proposed a new set of behavioral tasks that enabled us to have to compare humans and models on a sublexical level at scale. And these models helped us understand the role of contextual processing, specifically the directionality of contextual processing in speech perception. And we believe that these models could have good applications to study hearing loss. Thank you.